Um, Today we're going to be talking about vector embeddings, which is one of my favorite topics. This is what actually got me interested in programming and coding and machine learning. So I'm super excited to talk about this with you all. I need to figure out where to put this window. Hold on. Okay, here we go. And yeah, thank you so much to Data Science Dojo for hosting this and doing this with me. It's going to be fun. So I am Victoria Slocum. As she mentioned, I'm a machine learning engineer. I have a hybrid role. I do a lot of coding, but I also do a lot of community engagement and content. My background is actually in linguistics academically, but I got into machine learning, engineering, and coding and NLP stuff because of vector embeddings, because they are so cool. So I'm really excited to talk about them today. So when we talk about vectors, this is vectors are a mathematical concept, and this is just a list of numbers, and we can do certain math equations and stuff with vectors. But when we talk about vector embeddings, it's this machine learning concept of basically turning media, whether it's words, text, images, video, audio, into a numerical representation, a vector that represents its meaning. And we do this through vector embedding models. So today we're going to go over sort of what is a vector, how does that work, but we'll also talk about vector embedding models. I'll show you how to create your own vectors and your own projects as sort of a precursor for next week's webinar on vector search. And we'll go into how to choose the best embedding model for your project at the end. Okay. So the paper that I think sort of started most of this. Okay, so the research aspects, the academia aspects started maybe 2003, and they started doing a lot of research into vector embeddings and how you can represent words meanings with vector representations. And then this paper came out around 2013 about word2vec. And this was the first time that the sort of usefulness of vector representations was seen in sort of more industry applications. Stuff started coming out, and this sort of snowballed into the attention paper and everything we know nowadays, which we'll go into a little bit more coming up. So you can do a bunch of cool things with vectors. This is what really got me interested in machine learning. So let's take a look at some weird, cool things that vectors can do. Okay, so I mentioned before you can do math with vector embeddings of words. So if we take the vector embedding for queen and we subtract the vector embedding for king, weirdly enough, it's very similar to the value if you take the vector embedding for woman and you subtract the vector embedding for man. Kind of interesting. Let's look at another example. So if you take this is sort of a visual representation of vector embeddings. And so you can think of each little box as a color coordinated of the number of a vector embedding. So immediately what stands out is the vector for water looks a lot different than the vector for any of the other terms, right? And also, if you look a little closer, like your vector for woman and girl look very similar, boy and man look very similar, king and queen look a little similar. In water, you're missing this blue streak that is in everything else. For these terms, you have this green one, but that's different here. Super interesting visually, sort of encompassing what we humans have learned about these terms. So when babies learn what a word means, how are they figuring it out? How do they know what a woman corresponds to, what that word corresponds to? So what do these two things sort of mean? And this is sort of saying that these vectors actually are encoding the meaning of words in some way. Super interesting. Okay, let's take a break, go back to this in a second. For now, I want to talk about a different type of vector, RGB color codes. So RGB color codes are basically 3 numbers, and each number corresponds to how much red, green, or blue in a color. So every color is made up of various amounts of red, green, and blue. And then we use this basically in any design applications to determine different colors. You can make any color with the differing the values of red, green, and blue. So if you set every value to 0, you get black, right? There's no color. If you set all the values to the max value, 255 in RGB color codes, you get white. If you set red to the max value, you obviously get a red. If you set both red and blue to the max value, you get this lovely purple color. And if you set sort of a combination, you can get this color of emerald, right? So if we look at this in a 3D space, you can see here that similar colors are being grouped together, obviously, because they have similar values, right? So all the yellows are grouped together, all the greens are grouped together, the blues are grouped together, and more different colors are further apart. Okay, so each number is representing how much red, green, or blue is in the color. Funny enough, this is exactly what a vector embedding is when you're talking about vector embeddings in machine learning. It's a sequence of numbers that's representing the meaning. The main difference with RGB color codes is it's 3 numbers, right? And we know exactly what each of those numbers corresponds to, the red, green, or the blue. Vector embeddings are much higher dimensions. They can be thousands of dimensions, and we don't exactly know what number corresponds to what feature of the meaning of the word. There's been some interesting research done about this, but we can't be quite sure. But for theoretical purposes, for understanding purposes, you can think of each of the dimensions as encoding sort of a feature of whatever it's embedding. So maybe in the vector for cat, one of the numbers corresponds to if it's furry or not. Maybe one of them corresponds to if it's an animal or not, or if it has ears or not, different things like this. And the same thing happens with images or audio. Each of these numbers will encode a meaning of the vector, or of the word, or of the thing it's trying to embed. So that's sort of a high-level overview of what vectors are. This freaked me out a little bit. It took me a while to understand, so don't be concerned if you don't get it straight away at first. But for now, all you need to know, we can turn words and text and audio and video and images into this string of numbers that encodes its meaning, so that way we can use it in machine learning applications. When I first learned about this, I was like, okay, that's great, but like, how does that process actually work? How is something learning how to encode a text or an image or an audio into the string of numbers? Like what? And as I mentioned before, we do this through embedding models. So how do they actually work? I teased this a bit in the first part of the webinar. Word2Vec was one of the original papers where we got to learn, or where we got the idea that you could turn words into vectors through a method. And what Word2Vec was a neural network that learned word associations from a really, really, really big corpus of text. So it was initially trained with over 100 billion words, and these words were fed into this neural network, and based on the words surrounding it, this neural network was able to learn what this word means. There's a few problems with Word2Vec. We'll get into a little bit more how it works in a sec, but there's a few problems with Word2Vec. It embeds on a word level. There was a ways around this, but if you wanted to embed a full sentence with Word2Vec, it wasn't the easiest thing. You'd have to do some vector combination things. It also doesn't address words with multiple meanings. So for example, the word bank has multiple meanings. It can be the place where you put your money. It can be the place on the side of a river. It can be when you're driving really fast and turn, you're banking. It can be a verb. So it doesn't address those. Bank would just have one vector using Word2Vec, which is interesting. Okay, and they trained, or the way they got these embeddings from this model is they did a prediction model. And the particular prediction algorithm they used was called a skipgram. Basically, what you would do is you would input a word, and the model would try to predict the words surrounding it. So the words that came before it and the words that came after it. And surprising enough, when you train a model to do this prediction thing, it gets really good at learning what a word means, and then you can take that vector output and use that as the vector representation. Let's go into a bit more about that prediction thing, because it's kind of interesting, and I liked learning about it. Okay, so as I mentioned, let's make the data set for training our word-to-vec model. So we have the sentence, and basically what we're going to do is we're going to take an input word, and then our target words that we're going to use to basically score the model and how close it got to the target words are going to be the two words in front of it and the two words behind it, if that makes sense. So we can get a data set over here of all of our data. So not is an input word, that's a target word, that's what we want the model to predict. And for every input word, we get 4 target words. So then we're going to take our untrained neural network, our untrained model, and we're going to give it the task of predicting a neighboring word. So we're going to input not, and we want it to input our target, or we want it to output our target word of thou. And the model's going to do this. It's going to say, okay, not, I'm going to find that vector embedding. Then I'm going to take that vector embedding, go through all my math stuff in the background, and I'm going to output a prediction vector. And then we're going to correspond that to the vocabulary. So what word that prediction vector corresponds to. And our model chose to predict taco as its neighboring word. And we're like, no, that's not what we wanted you to do. So then what we do is we take the actual word we wanted to predict, and we calculate an error rate. So we're like, you got it really, really wrong. So you need to go back and update your model parameters. So that way, next time it's doing the same process again, it hopefully is going to predict thou, or at least get closer to predicting thou. And basically, we do this process lots and lots and lots of times over lots and lots and lots of data. And at the end, what it can do is take in new words and output vector level representations of these words that encode the meaning of them. Super interesting stuff. Okay. There's a link here of this whole thing. I really recommend looking at that if you're interested in learning more about this. I'll share these slides at the end of the webinar series too. Okay, so that was great, but again, there was these problems of it only embeds on the word level, and it doesn't do multi-meaning representations for the words. Some problems. Luckily, in 2017-ish, I think, we got this Attention is All You Need paper, which is probably the foundation of all machine learning nowadays. And these transformer models were super, super good at all the things, including vector embeddings. So this is how we got the BERT models, the ELMA models, all of these. This is basically what every modern machine learning model is based on. So the transformer models use the transformer architecture, which is described in this paper and very complicated. But basically what is different is it can take the entire input text into account, and it can modify each of the embeddings by the surrounding text. So it's not only using the 2 words in front and the 2 words in back, but it's using the entire text to make these representations, which made it a lot better. Limitations here are it was definitely more computationally expensive, but as it is the basis of all modern machine learning, whether that's large language models or embedding models nowadays, it's definitely worth it. So there's this paper, or there's this video on YouTube that I would definitely recommend watching if you're interested in this more. It's actually a whole series. Great, taught me so much. I've watched this video so many times trying to figure out how this stuff works. But yeah, we can see here too the example I had earlier, where it's encoding the meaning of these vectors in some way. So I wish I had time to go over transformer models in this talk, but unfortunately, time constraints, this would be a whole 45-minute talk on itself. So we'll move on. Before we get into how you actually create embeddings and use them, or before we get into how you actually choose an embedding model, I wanted to go over how you can create embeddings two different ways with Weaviate. So I'm going to go over to a notebook over here in Colab. The first one we're going to use is bring your own vectors in Weaviate. So with this notebook, we're going to generate embeddings with ModernBERT on Huggingface here. We use this model to generate embeddings and then insert them into Weaviate. So I've already done some of this stuff up here. I've installed the transformers library, datasets, and Weaviate. We're going to be using a dataset from my colleague Connor on archive paper machine learning papers. So I've just loaded all that because otherwise it would take too long during this. We're going to keep just the title and the abstract columns from this dataset. And then we're going to take, so the original dataset contained over 100,000 titles and abstracts, but for this demo, we're just going to take a random sample of 100 different papers. So that's this part, just taking a random sample. And basically at the end of that, we're going to get a dataset of 100 examples. And now we need to create embeddings. And I also did this before. I was hoping to do it during this, but it took too long. So I'm going to import the sentence transformers library here, set my model as the ModernBERT base model. And for every example, I'm going to generate a embedding and store it under the embeddings sort of property dictionary key for each example. And then I'm just going to map these embeddings into our existing data set. Okay, so when we do all this, we're going to get a data set, changing it to pandas. I'm really hoping this works. It's always a rough time. Oh no. I have to run all this again, I think. Oh boy, okay. Well, we're just going to do all this quickly. And hopefully it won't take too long. Yeah, and in the meantime, always live demos. You never know what's going to go wrong. Okay, so I think before we do this, then I'll go back to the slides, do the next section, we'll come back to it. Okay, pause on demo time. So how do you actually choose which embedding model to use? In the demo, we'll go over using two different types. So we go over using a open source model with modern embed base or ModernBERT base, and then we'll go over using one with OpenAI. But there's lots and lots and lots and lots and lots of different models out there. There's closed source models from OpenAI. They have a whole bunch. There's Cohere models. And there's so many different open source models that it gets really, really overwhelming when you try to figure out which one to choose. So how do you pick? There's two main things that you should think about here. The first one is data performance, and there's several subcategories here where you need to correspond it to your actual use case that you're building. So the first one is language specificity. Are you using this on purely English data? Are you using this for multimodal data? Are you using this for code? Do you need a really large context window? That all falls under language specificity. The second one is domain specificity. Are you using this on sort of general data? Or do you have a specific domain like medical, legal, e-commerce, where you need specific performance tailored towards that? Third one is, does it actually work? So certain use cases will require a higher amount of accuracy than other use cases. Or maybe you care more about accuracy on certain things than others. So you need to figure out how it works in general, and also how it works in your own data. So that's where benchmarking and comparison comes in. The second side of things is infrastructure. So as much as we would like it to be building machine learning applications is not free. And so this is where you need to think about inference costs. So what is it going to cost to store and interact with your model? Bigger models will cost more here. Smaller models will cost less. Storage costs. So when you actually create your vector embeddings, they can be different dimensions. And when you're storing those vector embeddings, larger amounts of or larger dimensions will cost more for storage. And the third one is the latency and throughput. So if you need a higher amount of latency, if you're doing more queries, if you need it to be faster, then you're going to need more infrastructure. So those are the kind of two sides of what you need to consider when you're choosing an embedding model. The MTEB leaderboard is a great place to sort of explore open source options and also explore all the different sort of tuning modules you can use and look at when you're choosing a model. So I actually just went on this site today and it looks a lot different than what it did when I made this presentation a couple days ago. But there's a lot of the same stuff in here. So they have different benchmarks now, different languages here. But we'll go over my slides and it corresponds still. So the first thing you should look at, and up in the top right, you'll see this, is the model size. So as I mentioned, larger models are going to be more expensive to run. Smaller models are going to be cheaper to run. If you have a billion parameter model, you're going to need to run this on some GPUs versus a smaller model, maybe 100, 200 million parameters. You can run that on a much smaller machine. So that's where model size comes into account. Second one is over in the tabs. You need to figure out what your use case is. What are you actually using the embeddings for? Are you using them for search systems? Well, then that's going to be retrieval. Are you using them to classify or cluster your data? Well, you need to figure out what that is and how the models perform in that specific use case. So certain models can be fine-tuned for different use cases. So it's important to see whether the model works and performs on your specific use case. Otherwise, you're going to be misled. So if we go over to the retrieval tab, because obviously I work at a vector search company, so I love retrieval tasks, we can look at all the models here. So on the left here, you have the model name. And for each model, you're going to have a model size. So the top models here are almost 8 billion parameters, which is huge. And you can also see the memory usage of this model. And this is also going to affect your inference costs. So how much is it going to take to run this model? What sort of infrastructure costs are you going to need there? Then over here, we have the embedding dimensions, and this is going to affect storage costs. So higher dimensional embeddings can often encode more meaning, which can help encode more nuances in the data you're embedding, which can often give you higher performance. The trade-off there is that higher dimensional embeddings are more expensive. So there's always this back and forth in machine learning trade-offs to think about. And then over on this tab, you'll see the retrieval performance. So this is an average of all the data sets over to the right, which we'll get to in a second. But how accurate is this model? When it does retrieval tasks, is it returning the things that is in the sort of gold standard data set? And this is where you need to look at all the trade-offs. Do you care more about having a cheap model run fast? Or do you care more about having the most accurate outputs? So things to consider. All right, and we have even more. So at the top there, you're going to see all your different language choices. So are you going to primarily use this for English text? Are you going to use it for multilingual text? Are you going to use it for code, long context, all of this? Things to consider. And then over scrolling right, you'll see specific domain data sets. So if you're using your model primarily for medical text, you're probably going to want a specific model trained on medical text. And this is going to help it pick up nuances in the data, learn which words are actually important to your data, etc. Something else we'll go over more in a bit, but is to take these averages with a grain of salt, especially with open source models. A lot of these data sets are public, and so a lot of the test data can sometimes end up in the model themselves. And so it's always, always, always important to do benchmarks on your own data in your own use case, figure out how it's actually working for you before you decide on a model for sure if you're using open source models. Okay, I'm gonna see. I think my thing should be done. And actually, I'm just gonna run this one too while we're doing the other one. Okay, so let's go through this now. Okay, so back to the demo part. Again, we've installed the transformers library. We're going to generate embeddings with the modern BERT model from Huggingface. We've kept 100 rows of this archive dataset. And if we look at the little dataset itself, you'll see we have the title, we have the abstract, and we have the text, which is a combination of both of those. And then we have our embeddings. Right. So next we're going to actually put this in Weaviate. And to do that, I'm going to use a sandbox from Weaviate Cloud. It's free, which is always good. So I'm going to create a cluster. So I'm going to go to console.weaviate.cloud. I have an account. I'm logged in, hopefully. Yes, I'm logged in. If you don't have an account, you can sign up for free. And then you click up, you can go to clusters, click on this button right here, create cluster. I'm going to create a sandbox. And I'm going to name it Embedding Demo. I'm going to select Europe because I live in Europe, and then I'm going to create. Awesome. So cluster is being prepared. And what we can do now is we can click on this connect button up top, and we can copy all of our info. So I'm going to copy the Weaviate URL here. I'm going to bring it back over here. And if you're doing this for real, please store these as environment variables. But for right now, I'll just paste them in there because it's fine if you access these. Okay, we're also going to copy the Weaviate API key here, bring it back over here as well. Awesome. And then we need to connect from here to our cloud. So I'm going to go back over here. And what's nice about this little button is it already gives you the code. So I'm going to copy this part, go back over here. I'm going to paste this part. And hopefully when I run this, it'll work. Oh, it might not work because I don't know if it's ready yet. Okay, still being prepared. Give it a second then. Do. Can I put some elevator music? Okay, while it's doing that, I'll go a little bit over the next part. So when that works, we'll have a client is ready. And then we need to actually create our collection within Weaviate to store our vectors that we just made in. So I've imported all the Weaviate stuff up here, and I'm going to define my collection name as Bring Your Own Vectors Collection, BYOV collection. And then this is just if I already have a collection, delete it. So then I'm going to initialize a collection by client collections.create, client.collections.create. My collection name will be the collection name. And then I have to set a vectorizer config, and we have our own vectors for this one. So we actually want to set the config to none. So then I'm going to do wvc.configure.vectorizer.none. And this is because we already have our vectors. So we don't want to actually vectorize anything within here. Is my cluster ready yet? Yeah, okay. Cluster's ready. Hopefully this should work now. Yeah, so client is ready, true. And then we can initialize our collection. Nice, run. Next thing we're gonna do is we're gonna insert all our data into this collection. So I've defined properties here. We have a text property and a title property. And then I can insert text, title, and also our embeddings into the collection. So by using this vector property. And I'm using insert many. And if I run this, it will put all of our data into the collection. If we go back into the cloud, reload this, reload this again, go to the Explorer and our embedding demo and our bring your own vector collection, we can actually see all of our stuff that's in Weaviate already. So we have our vectors here. Nice. We have our text, we have our title. Great. So everything looks good in here. Nice. Okay, let's go back to the clusters, go back to our thing. So just to test it out, make sure it works, let's do a little searchy through this with vector search, which we'll get into more next webinar, which you should also join. So my query is going to be which papers apply ML to the medical domain, and I'm going to return 3 results. I'm going to create my query embedding, so I have to embed this as well in order to be able to search through the vector embeddings. All the stuff has to be in vectors. So I'm just going to do model, which is the original BERT model up there, dot encode, dot query, and that's going to turn this into a vector representation. And then what I'm going to do here, pull up my notes, is collection dot query dot near vector. I'm going to do near vector equals query embedding. So I'm saying I want all the results that are near the vector, similar to the vector of my query embedding. And then my limit is just going to be top, and which is defined up here. And if we run this, we get our results. So the top 3 results are this, medical images, nice. General adverse neuroimaging, clinical neuroscience, again, nice. And this one was probably about medicine, but yeah, we're just returning the title here, but I'm sure if we return the abstract, it would also be about medicine. Awesome. So that works. So that's how we used a open source model with Weaviate with bring your own vectors. Now I wanted to go through a different example where we use OpenAI. This is also one where you can use Cohere, and this is where we're going to send our data through their API, since it's a closed source model, in order to generate the embeddings. So I did the same stuff up here. We have the same random, but not the same random, a different random data set of 100 objects. And now we need to connect to the cloud again here. So let me go back over here, click the connect button for the right sandbox, and copy our URL. And also copy our API key. And I've set my OpenAI API key as an environment variable in Google Colab because that's one I don't want you to see. So, but you can use it in Colab like this or use any other library in Python. So now we need to connect to the cloud again. So I'm going to copy this and paste it here. And there's actually one other thing we need to include here, which is a header. So if we go over to Weaviate's documentation and model provider integrations, you'll see all of our different model providers that you can use for vector embeddings slash generative modules. So OpenAI has text embeddings. That's the one we want to use. We'll talk about generative modules in the 3rd webinar. You should also join that one. And if we scroll down, we'll see here, this will be our header that we need to include in the connect. So I'm just going to copy this here, go back over here, paste it in there, and I named this slightly differently, so let's change that. Forgot to run this, but here's our different data set of 100 objects. And hopefully when I run this, we're going to get a is ready. Nice. True. Awesome. So as you can see, I updated the headers. It's the same collection, super updatable, very nice. And now we're going to create a new collection. This one's going to be called OpenAI Vectors Collection. Again, doing the same thing. If it exists, delete it. Now our vectorizer config is going to be different again. So we're going to do the same thing. Pull up my notes over here. You can find this in the documentation. Yeah, okay. Vectorizer config is going to be wc dot configure dot vectorizer dot text to vec underscore OpenAI parentheses. And that's it. So hopefully we run this. And again, we've defined properties. So we have a text and a title. And basically behind the scenes, what Weaviate will do is any data object that you import, it will automatically vectorize it using this config. So we run this, we're going to create the collection with those settings, and then we can insert our objects again here. This time we're not including the vector property because Weaviate is going to do that automatically. So let's do that. It's taking a little bit longer because again, it has to vectorize it. And then if we go to our cloud again, and then if we go to the Explorer tool again and choose our sandbox, oh, we have a new collection. If we click on that, we are seeing data. Awesome. Okay, and we can do the same little searchy thing. This time, instead of near vector, we're going to use near text because we have specified a vector, so we can just actually add the text directly. We don't have to vectorize it beforehand. And we get results again. Different results because it's a different data set, but that's why. Awesome. Okay, I'm gonna switch back over to the slides. Coming soon, there will be a third way to vectorize your data with Weaviate, which is Weaviate embeddings, but we'll talk about that in a second. Okay, so as we saw, there's the closed source option, which is the one we just did. The benefits of this is it's pretty fast, it's easy to use, it's a little bit simpler to implement. You don't have to host a model yourself. The drawbacks of this, though, is when you're using these, you sometimes will run into rate limits and you have to batch upload them and you're locked into the provider. So that can provide a little bit of a headache there. But again, easy to use. Open source options, benefits here are you have a lot of control and flexibility and visibility and open access. But the downsides here are you need to host it yourself. So hosting it is not free both work-wise and cost-wise. So you're going to have infrastructure costs, and this can take time away from actually developing your application because you have to develop or you have to maintain this model that's hosted. So we're introducing Weaviate embeddings in GA pretty soon. It's in preview right now. I'm super excited about this because what we're doing with this is we're hosting models within Weaviate Cloud, basically right next to the data. So you won't have problems with rate limits or batch processing that you might with APIs like OpenAI or Cohere. But you also will have the flexibility and control that you would with open source models, which will be super nice. Plus, less tools to worry about. I don't have to go over to OpenAI. I don't have to go over to Huggingface. It's just all in Weaviate. So we're super excited about this, both for our customers and for me, because it'll be development simplified. But Weaviate is really focused on providing developers and companies and anyone building AI applications as many options as possible, right? We don't want people to be locked in. So this is just another option for how you can build AI apps. Okay, in the last sort of 5-ish minutes, I wanted to do a little case study on one of my favorite embedding models, which is Snowflake Arctic Embed 2.0. Super interesting model. The paper came out pretty recently, and the researchers are doing some pretty cool things in training this model. But we had some also good questions. So if you look at the top models on the MTEB leaderboard, you will see that they're pretty big, right? I said 8 billion parameters. We're getting memory usage of 30, but we're also getting pretty high averages. So 68, 62, 62. However, if you look at the Snowflake models on MTEB, you're seeing kind of a different story. So your averages are going down. They're placed 36, 39, 43, 7% less. Why would you ever want to use something that's 7% less accurate on average? And the answer is if we look at the model size and memory usage, we get a much different story. So 334 million parameters instead of 8 billion parameters is going to be a significant difference in cost. And also, if we look at the outputted embedding dimensions, 1024 versus 4096, again, very different. So it's not only about how accurate a model is, how good it performs, but it's also about how much it costs to host it. Also, it's a really cool model. So this paper was super awesome to read. One of the best things about this is normally embedding models are really good at English or really good at multilingual data sets. However, what they were able to do by specific training procedures with this model was get a really good consistent performance with English and multilingual data set. So it has really high performance in English, but it also has really high performance in multilingual data sets, which is super interesting and novel and really, really cool. Another thing to look at here is that the Clef dataset is one of the datasets that doesn't often end up in open source model training. So it's not an open, it's a test dataset, doesn't often end up in models that are trained. And so closed source models like OpenAI's and Google's often do really well in this dataset, and open source models often don't do as well in this dataset. However, with this model, with the way they trained it, they were able to get good performance on this that's sort of on par with closed source models like OpenAI. The third cool thing about this model is it uses a really cool compression technique called Matryoshka embedding or Matryoshka representation learning, which basically allows you to shorten the embedding even more to save on storage costs. And it actually outperforms closed source models like OpenAI with this compression, which is super cool. So, just a few cool things about Snowflake Arctic Embed 2.0 as sort of a model case study, and why you need to watch for this trade-off between cost and accuracy. As much as we would want it to be, building AI applications is not free. It's not even close. And I think the important thing here is to remember that accuracy isn't everything, and to watch for those trade-offs and always benchmark on your own data and do use cases and all this. So I'm really excited for the next webinar next week because we're going to take all this knowledge on vector embeddings and translate it into something you can actually use and build with vector search. And the webinar, even after that, I'm going to talk about some agentic frameworks and other things, and that's also and use cases in the real world. So that's even going to be more fun. Super excited about this. Connect with me on LinkedIn. I talk about a lot of this stuff on social media, so super great. And I'd love to take some questions now. Um, I'm not sure if open source or open if Word2Vec is part of an open search protocol standards. Do I have a favorite embedder for multimodal? Ooh, Voyage AI is probably my favorite embedder for multimodal. We just released a integration here, and it's super, super cool. And yes, I will definitely send out all the notebooks and slides and everything, probably after all 3 webinars. So, but also, we actually have this one. I took this from the original source recipe. So Weaviate/recipes, you can find so much more than I could ever go over here. So everything from different integrations, um, AWS, to different Weaviate features. There's so much here. So I think we probably have a recipe for multimodal embeddings, hybrid search, named vectors. There's a lot more to discover here. Yeah. And coming soon, we'll have the Weaviate embedding service, as I mentioned. So keep an eye out for that. Any other questions? Can you shed more light on how to test different models on our data set and set benchmarks? What metrics we consider to test different embedding models? Yes, 100%. So my colleague actually has this great webinar. This one. Just watch this. That's all I can recommend. It will tell you everything from how to set up benchmarking, what you should look out for, all the things. It was a really, really good watch for me too. Because as a sort of more on the developer advocacy side, I don't necessarily build production AI apps, but my colleague Byron, who runs this, works with a lot of people who build production AI apps, and so he has a lot of insight on this in this webinar. What's the difference between a retrieval model and a re-ranking model in terms of embedding? Yeah, so retrieval models are what you use when you search. So if you're searching through a vector database, you're looking for similar vectors with retrieval models. Re-ranking models are after you have retrieved those results. They will basically take embeddings of those results and are more fine-tuned to then re-rank the results that you have retrieved before and return the best results. So it's more of an advanced process. Retrieval can get a whole bunch of vectors, and then re-ranking kind of fine-tunes that to get the most accurate results after. So it's just slightly different training processes that the embedding models go to then specialize in that sort of, what do I want to call this? Um, task. Task is what I want to call it. All right. Yeah, okay, great question. Benjamin asked about if we were parsing thousands of documents to swap in and swap out different LLMs dynamically, would it be best to bring your own embeddings, or is the embedding and Weaviate powerful enough? So I'm assuming you're talking about the embedding service. When we go uh, general access in a couple weeks, we are probably just going to be offering one or two models, but the plan is to eventually have more models there. So right now, not possible, but the embedding service in Weaviate will eventually be able to do this. Also, named vectors in Weaviate is a great thing for this because you can put multiple vectors on the same data item and then test those vectors out independently. But yeah, obviously bring your own vectors is always an option too. It kind of depends on what works best for you. Other than the MTEB benchmark, should we consider other benchmarks? Oh, that's a good question. Always be really careful about benchmarks. It's a thing that everyone looks best in their own benchmarks, right? If you're reading a paper, they're going to have whatever they're releasing the best in their benchmarks. It's one of the reasons Weaviate doesn't do competitive benchmarks because why? We're going to be the best. But honestly, the best thing you could do is do your own benchmarks on your own data. Even if it's super small scale, just get a feeling for it. Yeah. Are there any other Weaviate repos you recommend checking out on GitHub? Yes. Um, So we're working on doing some more projects, but I'm a big fan of Verba, which is our open source RAG demo that my colleague Edward has built. Super fun, great repo, very well documented. He just added the new DeepSeek model into Verba if you're interested in that, open source. Um, Open source, you can see all the things, and you can also test out our live demo with all the Weaviate documentation at verba.weaviate.io. But yeah, GitHub is also great. It's so pretty. Like, look at this README. It's great. What else? There's a couple other projects we have that are also linked in our demos page. Where is that? We keep moving around the menus and I can never find stuff anymore. Okay, not sure. But we have a demos page somewhere on this website that you can find where we have all of our demos. Oh, here. So Verba's here, Health Surge is here. We will be adding way more stuff to this coming soon. Lots of cool GitHub repos all over here. Um, what option do we have to use for data tabular, medicine data? There's lots of options for different domain data. Generally, as I said, there's so many different embedding models out there. In here, in the new MTEB leaderboard, you can actually choose like medical here and see all the best open source models for medicine. Boy. Okay, almost there. Yeah, so it'll go up here, but I'd recommend checking out this, checking out just doing Google search. Yeah, and you can use any of these models in Weaviate, so also good to know. Any other questions we have? Apart from training on our data, can you tell how we decrease the modality gap when creating different modalities and embeddings? Oh, good question. Yeah, multimodal data is still super tricky. Yeah, still super tricky. I mean, it's somewhat new and it's not an easy process to train embeddings on. Um, I'm not sure I have a super good answer for that other than try out different models, try out different embedding techniques. Yeah. And if you're interested in working with multimodal data, we do have a academy course on multimodal data, and this can get you started using the clip model, but then, you can replace that with others too. Tricky question. Anything else? Yeah, it's probably the Voyage AI, but uh, where was I? I was just on there, right? I don't know. Okay. Docs, documentation, model provider integrations, Voyage AI. Pretty fun. We also just implemented Kappa AI, which uses Weaviate on Weaviate on a Weaviate docs. So you can also ask questions, Weaviate specific questions here, which is super cool, and it's really good. Hard. If you were building a knowledge system that had to part thousands of documents. Oh, I think that question was already asked. Awesome.